All right. Last time we talked about a interesting property in isosceles triangles where AB squared minus AD squared equals DB times DC. And if the point D is on the extension of BC, then you would have AD squared minus AB squared equal DB times DC. Now these terms, DB times DC, where one segment times a longer segment, both coming out of the same point, or here, one segment times the other one on the opposite side. This is a very common pattern that shows up very often in geometry problems. And usually there is a circle that is not explicitly drawn right here. And that's what I'm talking about today. Imagine if there is a circle and then there is a chord. On this chord, there's a point D. Suppose this chord has 2 points here, B and C, then DB times DC, right, is the power of point at point D, right? Fits right here, right? So the question is, okay, how does that fit into our isosceles triangle situation? And where is the circle, right? That's more important. Where is the circle here? Where is the center? What is the radius, right? So let's see. If you draw a circle like this with A as center, AB and AC, both the radius, right? Because isosceles triangle. Okay. Now, what's the point at point D? What's the power of point D? The power of point D should equal to R squared minus AD squared. But in the meantime, the power of point at point D, the power at point D equal R squared minus the AD squared. And it also equal to DB times DC, because this is exactly how you learn it, right? Power of point, DB times DC. Now, if this confuses you a little bit, just in case this confuses you a little bit, then I'll show you why. Power of point, when the point is inside the circle, in the textbook, usually it says, it goes like, if you draw any chord passing through point A, then you will have a constant value of AB times AC. Okay, this is a constant. But what is the value of this constant then? What is it? It equals to R squared minus D squared, where D is AO. All right, D is the distance from this point to the center. So the power at point A equals R squared minus D squared, which equals AB times AC, right, which is a constant, right? It's a constant because radius is fixed, the circle is fixed, and D is fixed because A is here. AO equals D, right? And why is this true? R squared minus D squared, where does that come from? If you draw, you can draw all kinds of chord, right, passing through point A. Now, if you draw the special one, the one that passes through the center O, basically a diameter, right? If you draw a diameter, then AD times AE is also the power, right? AD equals what? Equals radius minus D. Radius minus D, right? Radius minus D. And AE equals what? Radius plus D. Their product is R squared minus D squared. Okay, just in case you don't know this, then now you know, and you should remember this. It's a very important result. And similarly, you can prove that if the point is outside the circle, then this is the power of a point, right? For point A. AB times AC equals D squared minus R squared. What is D again? D is the distance from that point to the center O, right? AO equal D. Try to prove it yourself. I think it's very, if you follow the steps here, it should be very accessible. Okay, now let's look at our isosceles triangle. So what happened there? What's the power at point D again? R squared minus D squared, right? R squared is AB squared. D squared is, well, that's our D here, no? AD squared. And that should be the power at point D, that which is then dB times dC. That's exactly what we proved last time, right? So safe to say that the situation in isosceles triangle is kind of like a special case of a power of a point inside a circle, right? There's a hidden circle with A as center. Think about it. All right. It was not explicitly shown, but if we draw it, we can see it, more clear, right? Now, if in the other case, if the point is on the extension of BC, not a problem. What's the power of point at point D? It's D squared minus R squared now, right? And this is D, the distance from the point to the center. It's the same circle, right? Still with A as center, and this is radius, right? So AD squared minus R squared is AB squared. And that's the power at point D, which also equals dB times dC. Okay, that's what we proved last time, right? That's it. A special case of a circle, and with this power of point at point D. All right, now, what about the example last time? So last time we talked about this problem. There's a triangle ABC where AB equal 86, AC is 97. This time, let's think about the circle. So a circle with center A, with AB with radius. So there's a circle like this, cutting BC at point X and keeps going, and there's a circle here. So this is an integer, what's the length of BC, right? Last time we connected AX and we solved it with the isosceles triangle property. Now this time, let's think about the circle. Let's think about the power of a point. Which point should we look at? Which point has a power that we should be interested in? There are not that many points, right? There's the center, the point B is on the circle, nothing to look. Point X is on the circle. If the point is on the circle, its power is 0, right? R squared minus D squared. D is R, then the power is 0. Nothing to look around here. Nothing to look here. Maybe here, maybe point C, right? Point C has a power, which is not 0. What is it? Think about it. If you look at the power at point C, it should equal to AC squared, D squared, right? That's our D here. D squared minus R squared, which is AC squared is 97 squared. R is AB, right? That's a radius. 86 squared, which is 11 times 3 times 61 that we know from last time, right? The rest is easy, right? This equals CX times CB, right? Power at point C, it's CX times CB, no? CX times CB. And then CX has to be larger than 11 and less than CB. So CX must be 33 and then CB equals 61, the same as last time. Okay, so this time I didn't even connect the AX, right? We just think about the circle, think about the power at point C, and we solved it in straight ahead, 1 second, like this. Write down this equation and problem solved. All right, next time we're gonna continue talking about another important application of this isosceles triangle property. All right, we'll see you next time.